Good afternoon, everyone. So this is my lecture in the continuation of my 9th lecture, that is based on electronic devices PN junction. So in this lecture, we are going to see how the PN junction is working, what type of biasing we can provide in the PN junction, and how these biasing will affect the location of the Fermi level below or above the conduction band and the valence band. So here we can see from the simple diagram that there is a P and N type of semiconductor to make a PN junction. So for making a P types of semiconductor, we have to add trivalent impurities. So by that way, we can create a P type of semiconductor. For the N type of semiconductor, we have to add a pentavalent type of impurity, and by that way we can create a P type of semiconductor. So by joining both these type of semiconductors, P and N, we can create a PN junction diode. So from the right side you can see a diode symbol which is shown here with a plus and a minus sign. So we can see from here that there is a diode in the right side and having a positive terminal and a negative terminal. So if you combine both P and N type of semiconductor, we can create a PN junction diode which is useful in various applications of electronic and semiconductor devices. With this PN junction diode, we can create our LEDs, we can create our lasers, and we can create our detectors also. So in the next slide, we can see how the PN junction has to be made. So as I have discussed that for making a P type of semiconductor, we have to create a P type of material. So semiconductor materials doped with acceptor type of impurities like boron, aluminum. So these have trivalent type of impurities, and with this acceptor type of impurities, we have more number of holes created in the semiconductor lattice or structure. So material has high hole concentration. We can see from the second point here, concentration of free electrons in P type material is very low. So electron concentration in P type of material is very low. So we have majority concentration is here, which is of due to holes, and minority carriers are basically electrons. So in the P type of material, we can see 2 points, that minority carriers are basically electrons and majority carriers here are holes. And what we have to add? We have to add here trivalent impurities. For example, trivalent impurities like boron, aluminum, etc. So we can include trivalent impurities in a pure or intrinsic type of form of semiconductor, and with these type of impurity or doping of the impurities, we can create our P type of material. On the other hand, how to create a N type of material? So for N type of material, the semiconductor doped with donor type of impurities. So these are basically pentavalent impurities. And with these pentavalent impurities like arsenic, antimony or bismuth, these type of impurities are basically pentavalent impurities, and this will create extra electrons in the lattice, and they are in majority of electrons is become the major part of the N type of material. So here the minority carriers are holes and majority carriers are electrons. So by this way we can distinguish between P type or N type of materials. Here concentration of holes in N type of material is very low, and concentration of electrons in N type of material is very high. So with this we can form a PN junction which can be useful in various applications as I have discussed. So in P type material, it contains negatively charged acceptor immovable atoms and positively charged holes basically. So total charge here is basically 0. Similarly, in N type materials contains positively charged donor which is immovable and negatively charged free electrons. So total, or you can say in equilibrium, we have total charge is equivalent to 0 in both the materials. It have majority carriers as holes and minority as electrons. It has majority carriers as electrons and minority as holes. So what happens if N and P type materials are in close contact? So when you touch both the type of semiconductors, P and N type of semiconductors, there will be some flow of electrons and holes from one type of region to other type of region. So if you are not providing any type of biasing, there is obviously no flow of electrons or no flow of holes from one part of the region to another part of the region. But when we provide biasing, then there will be some electrons movement from N side to P side, and there will be some holes movement from P side to N side. So there are some points which I have written here. Firstly, you can see from the figure that there are P type of semiconductor material and N type of semiconductor material, and we have joined both these semiconductor material to form a PN junction. So it has basically this terminal, and this terminal. It has three terminals, and the junction is only one. So junction is only one. So we have three terminals and one junction. So being free particles, electrons start diffusing from N type of material into P type of material. So there are two type of phenomena basically occur in PN junction, which is first one is diffusion and the second one is drift. So as the word suggests, that diffusion is, we have already discussed earlier, that diffusion is due to the change in the gradient of the concentration. Due to the change in the concentration gradient, we have diffusion of electrons from one higher region to lower region concentration. Similarly, we have another phenomena which is called as drift. So when you applied any electric field, under the influence of that electric field, there will be some drifting of the charge carriers or the movement of the charge carriers from one region to another. So obviously in the PN junction, we have both these phenomena. Diffusion will go by its own. On the other hand, for the drift, we have to apply some electric field. So we have to provide here electric field, which is obviously the applied electric field from the outside, but in the case of the diffusion, we have gradient, concentration gradient. So in the case of diffusion, we have concentration gradient, due to which there is flow of electrons from higher concentration to lower concentration. So these two phenomena will always occur in a PN junction. So being free particles, electrons start basically diffusing from N type of material into P type of material. Being free particles, holes to start diffusing from P type to N type. So there will be a diffusion of electrons from N type to P type, and there will be diffusion of holes from P type to N type. Having been neutral particles, eventually at the free electrons and holes had uniformly distributed over the compound crystal. So however, many electrons transfer a negative charge onto the P side, and also leaves an uncompensated positive charge of the donor on the N side. So we have the positive charge, we can see from the figure that the positive charge is living on the N side and a negative charge is on the P side, because it has more number of holes. So electrons will move from N side to here, and it will create a negative charge here in the P side, and similarly holes will move from P side to N side, and it will create a positive charge in the N side. So every hole creates one positive charge basically on the N side, and every electron will create a negative charge on the P side. So what happens if N and P type of materials are in close contact? So when they are in close contact, as I have told you, that the P type of material will create negative charge on the N side, positive charge on the N side, and N type of material create a negative charge on the P side. So we have this type of region will be created here, which is called as immobile charge carriers. So when the holes will flow from P side to N side, they will create a positive layer in the N side, and when electron will flow from N side to P side, it will create a negative charge on the negative layer of the charge on the N side, P side. So electrons and holes remains staying close to the PN junction because negative and positive charge attract each other. Negative charge stops electron from further diffusion. Obviously, when there will be a layer of the charge occur, then there will be no further diffusion from N side to P side. Similarly, positive charge is created on the N side, and there will be no diffusion of holes from P side to N side. So this diffusion basically forms a dipole charge layer at the p-n junction interface, and this particular width is basically depletion width. So there is a built-in voltage or built-in potential, we can say, at the p-n junction interface that prevents penetration of electrons and holes from p side, n side to p side and from p side to n side. So there will be some built-in potential or built-in voltage which restricts holes from getting into n side and electrons from getting into p side. So we will discuss this built-in potential and the space charge width in the later on lectures. So p-n junction current voltage characteristics, how the characteristic will come into in picture when we join p and n type of semiconductors. So what happens when the voltage is applied to p-n junction? When you apply some voltage to the p-n junction, as in the earlier side we have not applied any biasing, but in the next slide we have applied a biasing, that is a reverse bias. So we have provided negative charge on the p side, negative voltage on the p side and a positive voltage on the n side. So the polarity shown attracts hole to the left. Obviously the holes will attract to the left because it is a negatively biasing, and the electrons will attract towards the right because it has a positive biasing. So according to the current continuity law, what is this law? The current can only flow if all the charged particles move, forming a closed loop. Whenever there is a current, there must be a closed loop. Without that, there will be no flow of current, or you cannot imagine any current in an open circuit. There must be a closed loop for current to flow. So however, there are very few holes in an n type of material and there are few electrons in the p type of material, because n type of material have majority of electrons and they get attracted towards the positive terminal. Similarly, p type of semiconductor material have majority of holes which is getting attracted towards the n terminal or the negative terminal. So we have lesser number of electrons in the n type and lesser number of holes in the p side. There are very few carriers available to support the current through the junction plane. So that's why the current in this situation is very less, and it's not negligible, but it's very less in microamperes. For the voltage polarity shown, the current is nearly zero. So it's called as nearly zero, but it's in microampere range. So in the second one, we are providing forward biasing. So you can say this is a situation when we are providing reverse biasing. We are providing negative voltage to one terminal and positive voltage to the n side. What will happen when there will be a forward biasing? Second. So in the case of forward biasing, we are providing positive voltage to p type and negative voltage to n side. What will happen? The number of holes are in majority in the p type and they will get repel from the positive terminal. Similarly, the number of electrons are majority carriers in the n type and they get repel from the negative terminal. So they get repel and they will move towards the junction. So the positive having holes like this and the negative terminals having electrons like this, and they will cross the junction and they will create obviously the negative charge carriers on the p side and the positive charge carriers on the n side. So when they cross, they will provide you some current, there will be some loop and there will be some current. So as the polarity shown, this will attract electrons to the left and holes to the right. So there are plenty of electrons in the n type material. So obviously when the positive p type of holes will move towards n type, so there are plenty of electrons in the n type of materials and plenty of holes in the p type of material. They get interacted with each other and they will cross the junction. So when the voltage is applied is lower than the built-in voltage, the current is still nearly zero. This point is very important. So as I have discussed you that there will be some built-in voltage or a contact potential which you can say which is required to get the electrons movement from n type to p type or from p type to n type. So this VBE, we will discuss it later on, that is equivalent to KT by E ln ND NA upon NI square. So by this formula, we can calculate what will be the value of the built-in voltage when we having the number of donor concentration, number of acceptor concentration, intrinsic concentration. We can calculate the value of VBI. For the case of the silicon, we have VBI around 0.7 volts. So this is for the case of the silicon. So we have different values of VBI according to the donor and the acceptor concentration. So whenever it will cross a particular built-in voltage, only in that case the current will flow. Otherwise, below that voltage there will be a zero current. So when the voltage exceeds the built-in voltage, the current can flow through the PN junction, and obviously there will be a rise in the current as you increase the voltage in the forward biasing. So what we will see, we can have a diode equation or diode current voltage characteristic for the PN junction, which is given by this equation, which is also called as Williams-Shockley equation or the diode equation. So in this equation, we can see that I is equivalent to Is exponential QV upon KT minus 1, where K is your Boltzmann constant. T is your absolute temperature, and V is the built-in voltage. So we have Is is usually a smaller current, which is approximately 10 to power minus 17 to 10 to power minus 13. So we have the current flowing in the case of the forward junction, with which we can calculate with this formula. When the voltage V is negative, that is reverse polarity, the exponential term here becomes exponential negative to the power negative QV upon KT, and in this case the diode current, which is I, is usually very low, or it is around 0. When the voltage is positive, which is forward polarity, the exponential terms increases rapidly, and this will increase your current. So there are two situations. First one is when it is reverse biasing. So in the case of the reverse biasing, we have I very less in the or approximately equivalent to 0, and in the case of forward biasing, we have I very high, and it is approximately in milliampere, and it will increase drastically when you increase the voltage across the built-in voltage, when you exceed the built-in voltage for a particular type of semiconductor. Suppose you are using silicon, suppose you are using germanium or gallium arsenide. So for every semiconductor material, there is some different specific built-in voltage. So we have to cross that built-in voltage to make the movement of electrons and holes from one region to another for the case of the forward biasing. So we can see from the experimental IV characteristic, which you can also experiment in your lab with the help of the breadboard and fixing all the components like resistance or diodes and all, and we can see the voltage and current characteristic. This is voltage here and this is your current. So in the case of the forward biasing, 0.7 volt is your built-in voltage. So with this across this built-in voltage, below this voltage, built-in voltage, the current is 0, but when you exceed the voltage from 0.5 volt to 0.7 volt, there will be a sharp increase in the current. Similarly, in the reverse scale, we have a breakdown voltage, which is usually the Zener breakdown voltage, which we will cover in the later on lectures. So this is your Zener breakdown region. So at this stage, at the Zener breakdown region, we have a drastically sharp increase in the current in the negative direction. So we have this characteristic which we can draw easily in the lab by calculating the value of the current opposing to voltage, and by taking the reading from current to voltage in the case of the forward biasing, and again in the case of reverse biasing, we can draw the characteristic curve for the PN junction for the case of the silicon diode. So this diode IV relationship with some scales expanded and others compressed in order to get more details of the PN junction diode. So basically this PN junction diode will give you an idea of how the biasing will work, how the forward and reverse biasing will work, which type of components or semiconductor devices you can use in forward biasing, which type of semiconductor devices you can use in reverse biasing. For example, we have LEDs, we have lasers. So these LEDs and lasers, these are basically we can use in forward biasing. But when you want to use PN detector, pin photodiode, or avalanche photodiode, we can use in reverse biasing. So these type of two basically semiconductor devices like LEDs and lasers, which we can use in forward biasing, and the second one which are pin and avalanche photodiode, which we can use in the case of the reverse biasing. So these are basically more much important nowadays are semiconductor devices which we are using in many applications, in various applications. In the case of the laser, we have supercontinuum lasers, we have semiconductor injections lasers. Similarly, LEDs have other important roles, and the pin and photodiodes are used in lasers. Pin photodiode combination is used in fibers also. So we have semiconductor characteristics of this PN junction diode as I have explained you. Next, we have PN junction diode circuit notation. We have already discussed. We have a voltage source here, a resistance, which is basically to have a closed loop. There is a diode having positive terminal and negative terminal, because the diode have this type of, which is, this is positive and this is negative. So we are applying positive voltage to a diode, and there will be obviously flow of current across the diode. So when plus is applied to the P side, the current is high. This voltage polarity is called forward biased, or we have discussed already. When plus is applied to the N side, it is, the current is nearly zero, and this voltage polarity is basically reversed biased. So we have this type of characteristic curve in the forward biased region, where the current will automatically increase when you increase the voltage, but it has to follow the built-in voltage or built-in potential. So that particular built-in potential we have to cross. So PN junction diode applications, light emitters, as I have discussed that there are various applications like LEDs and lasers. So one type of this type of LEDs and lasers basically work in the recombination and generation process, which we will cover in the next 2-3 lectures. So we have this type of arrangement, that is P type and N type, and we already discussed that the electrons will flow towards P side when we apply the positive voltage to the P side and negative voltage to N side, and they will create electrons or the negative charge carriers on the P side. Similarly, the positive charge carriers on the N side. So electron drift into P material and find plenty of holes there. They recombine by filling up the empty positions. Similarly, holes drift into the N type of material and find plenty of electrons, and they will recombine there. They also recombine and filling up the empty position. So when these electron and hole recombine, they will release some kind of energy. So these kind of energy is basically in the form of the light. So whenever there will be a recombination process, there will be a generation of light or the emission of light here. And whenever there will be a breaking of bonds or breaking of holes and electrons from the recombined already recombined structures, then there will be a transmission of electrical energy or electrical signal. So the energy released in the process of annihilation produces photons and the particles of light, which I have discussed. So these lasers, LEDs and lasers, they will work in forward biased and they will create light. So in the next lecture, what we are going to do some photo detectors. So we will discuss about what are the different photo detectors and how these detectors are useful in the case of the semiconductor devices, to make some semiconductor devices feasible, so like fibers and all. So we will discuss in the next lecture about photo detectors and other components of the PN junction later on. Thank you so much.